So it turns out that if a matrix, specifically A, we're talking about the A matrix in a system of equations for pretty much all of these applications. It turns out if a matrix A can be reduced to a strict upper triangle matrix using only row operation 3, using only our elimination steps, then it is possible to represent the reduction process in terms of a matrix factorization. So we can represent this Gauss elimination process where we make our zeros in our lower right triangle, or lower left triangle, as A equals L times U, where L is composed of our multipliers from our elimination matrices, and then U is essentially our REF matrix, whatever we get when we end up with all of our lower triangle zeros. So the matrix factorization refers to a matrix written as the product of two matrices. We end up with an upper triangle matrix, U. So this is U. It's called an upper triangle matrix because our numbers are in the upper triangle. And then a lower triangle matrix, where we end up with these zeros in the upper right, but our numbers are in the lower triangle. So we have L times U in this instance. U is REF, like I mentioned, and L is full of my multipliers. Essentially the row operations that I used in order to put a zero here, a zero here, a zero here, etc. Like I said, we're gonna look mostly at 3x3s, but the process still applies to 4x4s. So in order to find the LU factorization, we are going to follow these steps every single time. Every single time, we are gonna follow these steps. We are going to find our first zero in the 2, 1 location. So we're going to find this zero. Using this row operation, R2 plus some multiplier of row 1. And then we're going to do this one, find a zero here. R3 plus some multiplier times row 1. And then we're going to find this zero by saying R3 plus some multiplier of R2. Once we do that, notice this plus sign here. Once we do that, what we end up with is our U. What we end up with is U. And then we're going to fill L. L always starts out like this. And then we just insert our multipliers. L21, L231, and L32. But we need to change the sign because it's actually filled with the inverses, and the inverse is the same. You just change the sign. There we go. We can get L, we can get U using our row operations. That's the first way to do it. The second way to do it is to know that this is what A looks like. This is what L times U is. So we know we want to end up with something like this. We know we want to end up with this same form every single time. So if I just multiply these and these together and leave it in variable form, I get this result doing matrix multiplication. So then I can just use equal matrices. So A11 equals U11, A12 equals U12, A13 equals U13. So given my A values, I can solve using equal matrices using LU. This is essentially a 9 system of equations, but we'll look at examples of both of these methods.